Video number 4 in the sequences series is what do we do if we have a sequence that is neither arithmetic nor geometric? Now, we are going to only look at a couple of special sequences. There are some sequences that you might not be able to find a pattern for or might not be able to find a pattern for easily. But let me show you a couple that I will be expecting you to know. The first one is 0, 5, 12, 21, 32, 45. It's clearly not arithmetic because you're adding different amounts between the numbers. It doesn't appear to be geometric either. A quick check, the fact that there's a 0 in there causes problems because 0 times any number would still be 0. So we couldn't even have a 0 in a geometric sequence. 12 over 5 and 21 over 12 are not equivalent to each other. So 5 and 5 over 0 is undefined. So it's clearly not geometric, it's clearly not arithmetic. So let's just look at what we do see in this. If it's not either, one thing to look at is another pattern. We notice here, if we say 0 plus 5 is 5, plus 7 is 12, plus 9 is 21, plus 11 is 32, plus 13 is 45. Notice that we're adding the odd integers, so the next one would be plus 15, plus 17. Also notice that if we look at the difference between the differences, it's plus 2 every time. Now hopefully some of you are saying, oh, I remember that. That's called the common second difference. That is a quadratic pattern. And it is indeed. If we looked at this table of values down here where I've written the term number n and the term a sub n as a table of values, we could see the same pattern, the plus 5, plus 7, plus 9, plus 11, plus 13, and then plus 2 each time. So how do we go about writing some sort of a pattern, writing some sort of a rule for this pattern? Well, we know in a quadratic function that f of n would have to be, well, let me just write it in terms of what we're familiar with f of x. So if we have f of x as a quadratic, we know that in a quadratic pattern, it can factor to x minus a times x minus b, maybe with some coefficient in front of it, but there's going to be some sort of a factorization that can be done. So the question is, what factorization do we have here? If we take a look at this, I'm going to find my notes here, because this one's a tough one. So with a sub n, we could think of this as a sub n is going to be n minus blank, or n plus or minus blank, n plus blank, or n minus blank, n minus blank, or something along those lines. It's going to be factoring where our term number is our input variable, like the x, and then when you multiply those two together, you get a sub n. So one thing to do to look for a pattern here would be to look and see is what are two numbers multiply together to give us some of these numbers. And I picked a fairly simple example. This one we could think of 45. Let's start with a larger number, 45. Well, 45 is 5 times 9. We could also think of it as 3 times 15, so there's other things. I'm going to start with 5 times 9 because I want to pick a number that's fairly close to 6 for the factor. So you'll see how this works. If we look at 32, 32 is 4 times 8. Ooh, 21, 3 times 7. 12, 2 times 6. 5, 1 times 5. And we could, for the sake of following the pattern, then we could say 0 is 0 times 4. So now let's take, since there's two numbers that are being multiplied together, let's look at both numbers and how they are related to the term number. So we have 0 and 4 related to 1. 1 and 5 related to 2. 2 and 6 related to 3. And I basically want to write it as something with two factors. So if we take the term number n, 0 is 1 less than n. Okay, 0 is zero is, let me get my little cursor going here so it's a little easier for me to, you see what I'm pointing at. So 0 is 1 less than 1. 1 here is 1 less than 2. 2 is 1 less than 3. 3 is 1 less than 4. So the first factor in all of these is 1 less than the term number. So we could start out with n minus 1 as the first factor. The second factor is 3 more than the term number. So 4, 5, 6 are 3 more than 1, 2, and 3, for example. So we could call this n plus 3. So if we, for example, plugged in 6, 6 minus 1 is 5. 6 plus 3 is 9. 5 times 9 is 45. So here's our pattern. It's quadratic. It fits the requirements. So this is something you can do with a quadratic pattern, is you can think of it as two numbers multiplied together, and then how do each of those two numbers, find a pattern, and how are each of those two numbers related to the term number. So there would be a rule. Notice that as an explicit rule, because I could plug in any value of n and find what the term is. There's also another way I could have done this, is I could have also set this up as a sub n is equal to n squared plus, we'll just call it, I don't know, I'll call it p, q, and r for the sake of having some variables. P times n squared plus q times n plus r. And I could set up 3 equations using 3 points. And my points being, for example, 1, 0, 2, 5, and 3, 12. And actually using 1 and 0, I would say n squared plus n, or p, I'm sorry, p times 1 squared plus q times 1 plus r. So p plus q plus r equals 0 would be my first equation. My second one would be p times 2 squared, so 4p plus q times 2, so 2q, so 4p plus 2q plus r equals 5. And then I would have 9p plus 3q plus r equals 12. So we did this back when we were trying to find equations. I could solve with a matrix. So that would be another method of figuring out what the quadratic equation was for this. Recognize once again, too, this is a quadratic formula, but we're only using values of n that are integers, so we can't just draw a parabola. It would just be a series of dots shaped like a parabola if we made a graph. Now the Fibonacci sequence is a much more unusual sequence. Some of you may have seen this before. If you haven't seen this before, pause a minute and take a look at the pattern and see if you can figure it out. It's very clever. If you can't figure it out, then turn the video back on and I'll show you. What you might want to notice is that you have to use 2 previous terms. In the past we'd say, okay, to get to the next term I have to add 2, or I have to multiply by 3. And I was always looking back at the previous term to find the next term. You can't really do that with the quadratic pattern. With this pattern, however, the Fibonacci sequence, you not only have to look back, you have to look back at the 2 previous terms. So if we look at 1 and 1 and think, how is that related to 2? Well, 1 plus 1 is 2. Then we look at 1 and 2. How is that related? Well, 1 plus 2 is 3. And then we have, see if I can bring a green one up here. And then we have 2 and 3. 2 and 3 is 5. 3 and 5 is 8. 5 and 8 is 13, and so forth. So our next term would be 21, and then 34, and then 55, and then 89, and so forth. So that's how the Fibonacci sequence works. Well, in the Fibonacci sequence, it's not arithmetic, and it's not geometric, and it's not quadratic. There isn't an easy way to write a rule, although an explicit rule does exist, and you can look it up or I can show it to you, but the generally used rule for a Fibonacci sequence is just by saying, okay, you have to add the 2 previous terms to get to the next term. So we have to start with 2 terms. So we're given that a sub 1 is 1, a sub 2 is 2. and then for n greater than or equal to 3, a sub n is equal to a sub n minus 1 plus, well, I need to go back one farther, a sub n minus 2. So for the first two terms, they have to be given, and I wrote down, another half-point opportunity missed for you here. A sub 1 is 1, a sub 2 is 1. For n 3 or greater, then we use this formula, a sub n equals a sub n minus 1 plus a sub n minus 2. For example, so I would say a sub 5 is equal to a sub 4 plus a sub 3. And a sub 4 would be 3. A sub 3 is 2. And so a sub 5 is equal to 5 in this particular sequence. That's how the formula works. The Fibonacci sequence is interesting in that it is found, these particular numbers are found in nature. You see them in the, commonly plants with petals have 13 petals or 8 petals or 5 petals or 3 petals. Not always, but very commonly in flowers. You'll see certain amounts of petals. They're found in spirals on the seeds of a sunflower seed or in the pattern of kind of little bumps on a pineapple. They're seen in the way certain things grow or multiply, the growth patterns. So if you looked up Fibonacci sequence on the internet, you would find a lot of interesting information about Fibonacci patterns in nature. So if you're interested, feel free to do that. This concludes the video on other types of sequences.